and linear. It's better to call them not vector, but linear. And linear morphisms. So since you're supposed to know linear algebra, so you know what linear space is and what linear morphism is, linear maps, and you know how to compose them. By the way, you know that sometimes they are invertible and sometimes they are not invertible. You may ask, how should I think about these linear transformations in the philosophy that it is an evolution? Let me share with you my knowledge on this subject. First of all, linear spaces appear from the mistake that teachers in the primary schools are making. So in the primary schools, at least in Russia, people often say, you cannot add apples with pencils. So people in the primary school obey teachers and forget that it is very natural to add apples and pencils. So here we have an apple, say 2 apples. And here we have a pencil. So it's very natural to put them together. So you will get a new object, a collection of 2 apples and 1 pencil. It exists. That's why we should include it in the description of the world. Okay? Now, since our world is not actually the world of apples and pencils, actually our world is the world of elementary particles. I know it because I am a physicist. So it's better to replace it as a collection of several particles. So you have several quarks, you have Higgs boson, say you have antiquark, okay? Maybe you have electrons. So this is naturally an object. How should you describe this object? You need to see how many electrons do you have, how many Higgs bosons do you have, how many quarks and antiquarks do you have. If you think a bit, you may realize that quarks and antiquarks can annihilate. Okay? And electrons and positrons can annihilate. So actually, if you want to keep this box, you need to find the number of quarks moduli, the number of antiquarks. And this is actually the origin, physical origin of negative numbers. Unfortunately, people had to invent them like 500 years ago because they never heard about antimatter and annihilation. But now, when we know about it, it's clear that negative numbers are naturally in our world. They exist in the form of antimatter. Okay, so this is an object. And this object, suppose I have electrons, quarks, and Higgs. I can form the following structure. Chi-e is the number of electrons, K-q is the number of quarks, and say K-Higgs. Okay, I would not like to talk about Higgs boson because you don't know at the moment what it is. But you definitely heard about electrons and quarks. By the way, in my course, I'll explain to you what the Higgs boson is. So now we have electrons and quarks. Okay. Now, what is a linear transformation? A linear transformation is the following. You have the set of elementary particles. And then just imagine that after some period of time, some of these particles can decay. Okay? But each particle decays independently on other particle. So what I'll get is, after decay, I get what? I get a linear transformation. You can consider electrons and quarks as elements of the basis, and basis is transformed into linear combination of other elements of the basis. Actually, here I consider universal basis. I include here all elementary particles. So, in this way, I describe big N by N matrices. It is a result of the process of evolution. So N stands for all types of elementary particles. Still, I have special objects where some of the particles are not present. So, like E. Here I have no quarks. Or Q. No electrons. So these are special objects. Okay? So you may think a bit, and you will see that the category of linear spaces is actually the category where we put in all possible ways of decaying a particle into combination of other particles. So morphism you may consider it as a map, but you may also consider it as a decay process. Okay? That's why the morphism is actually a motion. So you may think about it, or maybe you know it. By the way, that's why it's another explanation why the composition of morphism is associative. But now I want to move to another concept, and this is a concept of functor. Maybe you realized that I never introduce a concept without motivation. Okay? So mathematical concept is an attempt to formalize something in our real world. And when this formalization is successful, and it happens in many cases, you are starting doing math with it, okay? You are starting using this concept. And if you are formalizing something stupid that doesn't have origin in the real world, you may be sure that the crazy axioms that you are giving would not be useful later on, neither in physics nor in mathematics. So you formalize some event in the mathematical world or in the physical world. So I'm coming to the notion of functor. Actually, I'll call it covariant functor. So the notion of covariant functor has its origin in the set theory. Because you see, the object is something like a set. So once again, object is something like a set, and the morphism is something like a motion of the set. So it's logic. So in the set theory, we have actually two different processes. First process of the set theory is surjection. Actually, you take a set and you take a quotient with respect to some equivalence relation. Okay? So it means that you are identifying collection of elements. So you come from A, B, C, D, E, this set, to a set of subsets, say A, B, C, D, E. Because you somehow so A is identified with B and C is identified with D. So in physics or in any imaginary world, it means that you are forgetting some properties of the object. So you forget the distinction between A and B, distinction between C and D. But now you consider the motion of the set or evolution of the set. Then just think what would happen if this evolution, if this motion is coherent with this identification. It actually means that things that were identified move coherently. So it is one way to define a functor. So it is like surjection or forgetting something. Now, there is another way in the set theory. So you have, say, collection of objects, A, B, C, and you see that it belongs to the bigger collection of A, B, C, D, E, F, G. You have inclusion, injection. Now, let us add motion to it. here you have motions. And here you have motions. You may say that everything is coherent if motions of the big set coincide with the motions of the smaller set. So you include, say, this set and its motions into the bigger set and their motions. So this is kind of an explanation from the set theory. So it's inclusion and surjection. Let me give more examples of this phenomenon. First example is this. Suppose we have, as you may expect, category of smooth spaces, okay? Objects, smooth spaces. And morphisms are smooth maps. Let me say, let us consider here objects not only smooth spaces, but smooth spaces with fixed point. So here I have spaces with fixed point. Now, morphisms would be smooth maps that map fixed point to fixed point. So very good category. Now, you may consider the tangent space to X at point P. So if you have a smooth map, you map it to tangent space of X tilde at point P tilde. And we call it derivative of F. So here is a theory of maps. And here is a theory of, so this is actually category of linear spaces. Because object is a linear space and morphism is linear. So actually it means that you forget something. You forget the existence of other points, almost. You are remembering only points that are close to P. You are forgetting a lot of information about F. So you go from something that is big to its characteristic, but everything is coherent. Okay? So this means that I go from objects in one category to objects in another category, and I go from morphisms in one category to morphisms in another category, such that everything is coherent. And this is the example of a functor. So if you think, you can imagine many other functors of this type. Okay? Now, remember, we have another example of the category. It was about, sorry, not maps, but another kind of maps. Remember, when we have a continent and the roads from A to B to C, okay? So actually, here we have roads in the real world. But now we have a geographic map. And here we have a picture of the continent. And here we have lines drawn on this picture. So this is a physical object with a lot of data. It's a continent. And here is a map. And what's important is that you may, when you are traveling, you are looking for the trajectory here. And you see that it corresponds to trajectory here. So if you have a proper map, if you can go from A to B and B to C in the real world, you can do the same thing on the map. So this is, say Eurasia, okay? Now let me say something else about this example. In particular, in the real world, I can have also paths. So this is a road for a car, and here you can walk. You just don't draw these roads here. Still, it's okay. In this map, everything works. So you forget a lot of information when you go to geographic maps. However, a geographic map of Eurasia is a piece of the geographic map of the world. That has map of Eurasia, and also it has map of America, and also a map of Australia. And in this big set, you have, of course, A, B, C, but you have other objects, some cities in America, and some cities in Australia with their roads. So, of course, you have this inclusion functor here. These objects belong to the set of these objects, it's inclusion, and these roads belong to the set of these roads. So these are the examples of covariant functors. So mathematical definition is that you have a category. So it has objects and also morphisms. So functor is a map from, So you have category with objects and morphisms. So these are sets. And you have category tilde with objects tilde and morphism. So the functor is a map that contains of the object map. It takes object to object tilde. There is also a morphism map. It takes morphism, space of morphisms, to morphism tilde. Now, coherence. So coherence is clear that what you can do, you can have a map, a morphism from A to B. So I go from the right to left. I'm sorry. And I can compose it to morphism A to B from B to C. So this is a composition. This belongs to morphism of from A to C. Here is the space of morphism. And here we have, say, morphism M1 and M2. Now, what we can do? We can first take the morphism and map it into other category and compose there. Or we can compose here and then go to other category. So f of M1 BC, so it's a functor, M2 AB equals to, and here the composition I'm making in category to the functor of M1 applied to M1 between B tilde, C tilde, M2, A tilde, B tilde. And here composition is in category tilde. So this is the axiom of the functor. And here are examples to show you that this axiom just formalizes natural things that happen. Once again, naturalness. By the way, the word naturalness is relative to the word nature. Naturalness means something that happens in nature, that happens in our world. If you say it happens in mathematics, it's okay, because mathematics is natural. Mathematics is a derivative of our world, okay? So there is a philosophical functor. So there, okay. So here is philosophy. No, philosophy is written. I forgot how philosophy is written. Maybe like this. and be like this. So philosophy of naturalness. We have nature and we have mathematical physics. And we have kind of a functor. It takes objects in nature to some objects in mathematical physics. So it is functor of my science. That's why mathematical physics is called physics. So relations in nature correspond to relations in mathematical physics. Okay, so this is philosophy. I am not professor of philosophy. I'm professor of mathematical physics. So this is kind of a picture, and this is a mathematical definition. And this is called covariant functor. Okay? So it's very easy notion. Now, and this is the last thing that I was planning to tell you today, is the idea of contravariant functor. I am not going to give you definition at the very beginning. So on the level of definition, things are simple. So you can say, you can check that definition is correct. However, this definition, if I just give you formal definition, would look very unnatural. And now what I am going to talk about is the naturalness of the definition of the contravariant functor. Okay? Naturalness. So I come to motivation from set theory. So when we consider sets, it's a collection of elements. There are two ways to construct a set. One way is to find a constructive algorithm that creates new elements from elements, say by induction, if you wish, or just enumerate them. So when I say set ABC, I just say this set that contains of A, of B, and of C. Another definition of the set in this way is the definition of natural numbers. So you consider the empty set, then you consider the set containing of the only element that is an empty set, then you consider the set whose elements are this, okay, and the set, the only element of which is this set, and so on. By the way, this great definition of natural numbers was given in the ancient Greece 100 years, approximately 100 years before Christ. So they did not know what the set theory is, but they said that natural numbers could be considered from nothing. They said, suppose we have a nothing. Suppose we have something whose only element is nothing, and so on. So here is a set whose element is nothing and the previously constructed set. So it is a way how to construct natural numbers from nothing. Okay, so you can construct sets in this way. However, you can construct set in another way. Suppose you have a set C1. Suppose you have a map from C1, it's a set, to set constructing from two elements. I say yes or no. Okay? And then, and I will call it this function. Okay? And then I can consider a new set that I call SF. So SF is a set as all elements A belonging to set S1, such then function of A, the value of function, is yes. Okay? So this is very natural way to describe sets. Just imagine how we describe sets. Like, suppose that S1 is a set of natural numbers that we already know how to describe. Then we can consider a set of even numbers. We ask a question. So this is a question. If number is even, so if answer is yes, then we put it to this set. If answer is no, we do not put it to this set. Okay? In this way, we have an interesting correspondence between the sets and questions. Okay? And it is very interesting correspondence, because the more questions we ask, the smaller the set is. So let us consider an example. So suppose that we ask two questions. Okay? Question F2 means divisible by 2. Once again, to yes, no. is a number. Okay, so here I can even put natural numbers. It's an example. Is a number divisible by 2? The second question, of course, is a number divisible by 3? And we also have this. Now we impose 2 questions. Now, please note that we have questions, and questions also form a set. Okay? So we have n f2, n f3, and also n f2, f3. Now, let us think. What happens with the natural morphisms in the theory of sets that are inclusion? Just think. You see, the more question you ask, the smaller the space of solutions to these questions, or where you get answer yes is. Okay? So F2 belongs to F2, F3. What is the relation between n F2 and n F2, F3? How do you think? If you give answers to both questions, F2 and F3, you definitely give answer to the question F2. We have an interesting phenomenon. It's called inversion of arrows. So here we map. Actually, we map in this way, from question to set. However, the more question we ask, the smaller the set is. So maps or morphisms are inverted. So suppose we have F1, okay, F2. It is inside F2, F3. It is inside F2, F3, F5. And here is the space of answers, or not answers, of sets that satisfy these properties. In my example, it's being divisible. We have inclusions like this here and opposite inclusions here. And this is an example of contravariant functor. The more equations, the less is number of positive answers. Of contravariant functor. By the way, I told you that morphism is evolution in time. So you cannot actually, in general, invert evolution in time. So that's why, while formally you can write this definition, it's very hard to have a model. And this is the natural model of contravariant functor. So now I'm ready to give a definition. You may give it yourselves. So contravariant functor is a map that goes from objects to objects, F object. It goes from morphisms to morphisms. That inverts the order of errors. And you can write formula yourself. So I evaluate your time very much. And when I'm saying something, I should answer the question, where are we going to use it? So later on, we will immediately use contravariant functor in algebra geometric description of spaces that we will need later on to understand what supergeometry is. And we will use covariant functor in the definition of what quantum field theory is. So once again, when I'm telling you some general nonsense, I'm telling it to you on purpose. And I'm ready to explain why you, suppose you are a physicist or a mathematician that is working on definite problem. Why you have to study all this garbage? Because it will be immediately used. Okay, now it's a time for questions. Yes, so
Well,
good comment. In philosophy, it was I here. Okay. It's a time for
Can you
questions.
hear me?
We have like 5 minutes for questions, comments, anything. Written
Can you
or
hear
oral.
me?
Yes.
Okay, I have a question. Is a functor an isomorphism?
Functor is not isomorphism, because in the functor, we are forgetting a lot. So there was an example. There is a real continent and there is a map. When we do this type of functor, we are forgetting many things. So
okay,
it is like...
Then finally, final category can be bigger than previous category, yes? So we can say that math is bigger than nature.
Exactly, yes. Yes. So, but it's not actually bigger, because there is a philosophical theorem of mathematics that everything could be made out of surjections and injection. Okay, so relation between math and nature is as follows. So here we have nature. Here we have math, or what I call mathematical physics. Actually, if you think a bit, you would see that there is no difference between mathematical physics and mathematics, because mathematics is the mathematical physics of the past. Okay? So we have this functor. In this functor, we forget something. Okay? However, this functor is not surjective. In some sense, math is bigger than the image of nature. So it's this picture. Nature, image of nature in mathematics, and something else. And this something else is imaginary worlds. So in this language, mathematical physics is studying imaginary worlds and relation among them, such that if we map nature here, it would be a functor. Covariant functor. So did I answer your question?
Well, yes.
Good. By the way, I see that mostly Russians ask questions. And you see, maybe it's because Russians are not afraid to ask questions. But without asking questions, you will get nowhere. So please ask questions, comments, everything, anything, whatever you wish. Okay, so please write down questions, okay? So if you're afraid to write down questions, I will make a forum, so you can have a nickname, and being under nickname, you could ask questions. Even right now, you can make an email address, extra email address. Call yourself, say smart boy or smart girl, and send me questions. And I'll try and I'll reply. I actually need it to make this course better, you see? Okay. Satori is not translatable to English. Okay, so English speaking people know what Satori is, because Buddhism and a bit of this philosophy is known in the West. So, Miss Hu, you know what Satori is, so I know what Satori is, so we can communicate using English words. Okay. So I invite you to come to the next talk on Tuesday. That would be on 4 p.m. 4 p.m. Beijing time. And it is 11 a.m. Moscow time. And if you are coming not from China or from Moscow, you can compute. And I'll speak about physics. Okay? Well, thank you.
Well, goodbye.
Goodbye.